Okay. Okay, so back here to talk about mappings. The first thing we're going to want to talk about is an ordered pair. So if you guys remember from most of the classes you've taken in the last few years of math, these guys are not the same. 1,4 is not the same as 4,1. That's because in this case, order matters. We're talking about these as points, not as sets in interval notation. These guys are not the same thing. And we can give that a rigorous definition, using our sets that we already made. And that would just be that AB is equal to A EB. So this right here, you don't really need to know this, but it's good for you guys to know that there is a rigorous underpinning for this, and that's how we define an ordered pair generally. The Cartesian product, A cross B, is going to be the set of all ordered pairs of elements of A and B. So to give an example, if we have A is equal to 1 and 2, B is equal to RGB, then A cross B, I don't know what's going on here, is equal to 1R This right here is the Cartesian product. It's the collection of all of these ordered pairs. So if I want to define a mapping generally, it's basically just going to be a subset, a mapping is a subset of A cross B. So we might say we want the subset that's defined by these three guys. And that would be so this would 1 maps to R, but also maps to G, and then it maps to 2 maps to R. So this guy right here is a mapping, but it's not a function. For it to be a function, it would have to have only one arrow coming out of each of these guys. This guy has 2 arrows coming out of one. So this right here, that's fine, that's a function. If we have the ordered pair 1R, 2R, that's fine. That is a function, but this is equivalent to the vertical line rule. So if we have a mapping from R to R, and it looks like this, that right there is a function, because for each thing in the x domain, there's only one thing in the y domain, which is equivalent to saying that if I draw a vertical line, at no point does it hit two different elements of my function. But if I have here, I can draw a vertical line that passes through the mapping, which tells me that this right here is not a function. And that's the same thing as saying that if, let's say this point is, the x value here is -3, that there are multiple things that -3 maps to. And if we have one element in our starting domain that maps to multiple elements in our end domain, or in domain versus range, if we have one thing in our domain that maps to multiple things in our range or codomain, then we know that this is not a function. So for the most part, we will only work with functions or inverse images of functions. So that means that we won't be dealing with general mappings terribly often. So injective, what does it mean for a function to be injective? It means that each element of the domain maps to a distinct element of the range. So if we've got A, B, 1, 2, R, G, B, this guy is injective because they do not map to the same element. But this guy is not injective. An equivalent thing to say here is that the inverse image of the function is also a function. In this case, because each of them is no two elements map to the same element, then when I go back for the inverse image, each element only maps to a single element, versus here, the inverse image, the inverse image R maps to both 1 and 2, meaning that it would not be a function. In terms of surjective is, so this means that the cardinality of the starting set is less than or equal to the end set, as we can see in this case, that we have the 1 and the 2. So this guy clearly has cardinality 2, this guy clearly has cardinality 3, and it's impossible for, if my starting set, if the mapping is injective, then it is impossible for the starting set to have a greater cardinality than the ending set. Surjective means the opposite, or surjective implies the opposite. It's that this guy, that the end set cannot be bigger than or equal to. So surjective means I cover the entire set. Think of it like a troop surge is meant to cover the entire thing, or a surge of water can flood your basement. So if we have 1, 2, 3, red and blue. So in this case, this mapping is surjective because it covers every single element in our range. This guy would not be surjective. So that's an important thing to note, that just the fact that we have a mapping that is not surjective or not injective, that doesn't tell us anything about the cardinality. But if we have a mapping that is surjective or injective, we do know something about the cardinality. So we can also look at the question of bijectivity, which means that we have a mapping. A mapping is bijective if it is both surjective and injective. Also, I've got these little one-to-one and ontos. A lot of the time you'll talk about, instead of a surjective function, you'll talk about an onto function. Instead of an injective function, you'll talk about a one-to-one function. I prefer the injective and surjective, but they're pretty common also. So bijectivity, if I have 1, 2, 3. This guy right here would be a bijective function because every single element in the range or in the codomain is covered. Every element in B is hit by some element of A, and it's hit by exactly one element of A, which that tells us that the cardinality of A is greater than or equal to the cardinality of B, and also the cardinality of B is greater than or equal to the cardinality of A, which means that the cardinality of A is equal to the cardinality of B. That means that they have the same number of elements in them. And that is actually, so in finite case, that's pretty easy to see here. But in the infinite case, that gives us some weird results. So this is actually going to be how we define infinite cardinalities, that they correspond to, that we say that two infinite sets have the same cardinality if they can have a bijective mapping, if you can find a bijective mapping. So let's say we want to prove that the cardinality of the integers is equal to the cardinality of the natural numbers. Then we have to find some way to map between this and this. So a natural way to do this would just be first one's 0, and then I go to the next positive number, and then I go to the next negative number. Then I go to the next positive number, and then I go to the next negative number. And I keep on doing that. So I alternate back and forth between which one is positive and which one is negative. And so in this case, I have a function f from n. So function f of x from n to z is going to be defined as f of x is equal to -1 to the x plus 1, right? Because we want 1 to correspond to a positive number. So that means that we're going to have this right here as an even power. times we'll do this as floor of x over, sorry, no, we want ceiling of x over 2. Ceiling of x over 2. So that means that when I'm dealing with 1, I'm looking at the ceiling of 1/2. Ceiling of 1/2 is 1. When I'm looking at 2, I also want it to come out with 1, just corresponding to the negative version. And the ceiling of 2 over 2 is the ceiling of 1 is just 1. So that tells us that the natural numbers have the same cardinality as the integers. That's how we define it. We can also do a proof that the cardinality of the natural numbers is equal to the cardinality of the rational numbers. And to remind you guys, the rational numbers look like P over Q, with P and Q in the integers, Q not equal to 0. So it's anything that can be written as a fraction, basically. So how are we going to do this? Well, we can write every element of, we can do 0 over 1. Sorry, you should be over 3, 2 over 4. Sorry, 1 second, I'm blanking. So as we go out this way, the top increases. As we go out this way, these should all be 1s. Sorry, that's what was messing it up. As we go down, the bottom increases. As we go right, the top increases. 2 over 4, 2 over 5. So this and then we can also do negative 1 over 1, negative 1 over 2, negative 1 over 3. This actually covers every single one of our fractions infinitely many times, because 1/2 is equal to 2/4 is equal to 3/6 is equal to 4/8, blah blah. And also, clearly the natural numbers are smaller than or equal to the rational numbers, because every single natural number is a rational number. 1 is a rational number. 2 is a rational number. 5 is a rational number, blah, blah, blah. So if we can just show that there is a mapping that covers, from the natural numbers, that covers all of these guys, that tells us that the natural numbers are greater than or equal to the rationals, even if it's not injective, even if it's not 1-to-1, that still means that we'll have that the naturals would be less than or equal to the rationals, and also that the rationals would be less than or equal to the naturals. And in case you're wondering, the Q is for quotient. That's why we call it Q. So first things first, we're going to set 0 and assign to this guy. And then we're going to go around in order. 1 goes here, 2 goes here, 3 goes here, 4 goes here, 5 goes here. And then we're going to continue wrapping around. And we're going to continue wrapping around. And that means that any one of these representations will be covered by a finite element of the natural numbers, which means that the natural numbers, that means that we have a mapping from the natural numbers to the rationals, even if it's hard to, it's not one that we'll write out as a nice f of x is equal to function of x, or is equal to like x squared or something like that, or how I was able to come up with this guy right here. We won't get anything that nice, but that doesn't matter. We still have every single element of the naturals corresponds to a unique element of the rationals, which means that we have a function, and we also know that this function is surjective. That means that it covers the natural, or that it covers the rationals. Therefore, we have that the rationals, the cardinality of the rationals is going to be less than or equal to the cardinality of the naturals. And also the fact that the naturals are a subset of the rationals clearly tells us the cardinality of the naturals is less than or equal to the cardinality of the rationals, which means that the cardinality of the naturals is equal to the cardinality of the rationals. And all of these guys that we've done so far have been what are called countable infinites. Meaning that we can put them we can find a bijective function mapping them to the naturals. It basically means that you can just put them in an infinitely long list with a starting point. But turns out that's not the only size infinity that we have. We also have something called uncountable infinities. In fact, most infinities are uncountable. We just have the one countable infinity, and we have infinitely many uncountable infinities. But there is one set that we're very used to working with that turns out to be an uncountable infinity, and that is R. And the guy who discovered this is a guy named Cantor, and he kind of broke math when he discovered it. This is a sketch of the proof that he used. Assume this is going to be your first exposure in this class to proof by contradiction, which means we assume the opposite of the thing we want to show. So assume that there exists, that's what that backwards E sign means, a function f such that it is a bijection between the natural numbers and the real numbers. So that means we would have 1 is equal to, say, 0.084573. 2 is equal to 0.093642. 3 is equal to 0.9874512, blah, blah. Is equal to 0.896327, blah, blah. And each of these guys goes off to infinity because we've got the infinitely long decimal representation. So, and that this list contains every single element of R. I'm going to get a contradiction by showing that it cannot contain every single element of R. And I'm going to get that by constructing something off of this list that cannot be on the list. And to do that, I'm going to say, look at each element of the list and change the nth element, or the nth digit, by adding 1 with 9 goes to 0. So in the first case, so given this list that I just drew up, I would look at this guy and I would say, okay, I have a 0 here, so that means I have to change that to a 1. Okay, I have a 9 here, that means that I have to change this to a 0. Okay, I have a 7 here, that means I have to change this to an 8. Okay, I have a 3 here, becomes a 4. And that tells me that this number is going to differ by exactly 1 digit from every single element in my list. That means that it can't be equal to any element of this list, which means that this mapping does not actually cover R. Therefore, this is not in the image of F. Therefore, F does not cover R for, which tells us that no such function exists, bijective function, or surjective function, from, because we can do this with any F that you give me, any F, not just, it's not just arbitrary based on these guys. Any single F that you give me, this system of looking at the nth element of the list and changing that nth element, or that nth digit, by adding 1, that is going to generate an element that is not in the image of your function. Therefore, F does not cover R. No such F is going to be surjective from the natural numbers to R. Therefore, they're not the same cardinality. In fact, cardinality of R is strictly bigger than the cardinality of the naturals. Which tells us that there are, in fact, different size infinities. And this is going to be your first exposure to an uncountable infinite. There is another very interesting proof that I actually just stumbled across for the first time the other day, that there can be no function that maps from the natural numbers to R. I will link to that in the video playlist that I will send you guys. So another thing to note is like 2 things to note, I suppose, are, first off, that the power set of a finite set A is equal to, or the cardinality of this guy is equal to 2 to the cardinality of A. This is going to be strictly greater than the cardinality of A. So that tells us for every single finite set, the cardinality of A is going to be greater than the cardinality of the power set of A is going to be greater than the cardinality of A itself. And it turns out that this is also going to actually work for infinite sets. And we'll sometimes still write this as 2 to the cardinality of B, even though this is a bit less well-defined. This doesn't correspond to an actual number in the same way that this guy corresponds to it. It's basically just, this is how we denote a specific infinity. And it's going to be a bigger infinity than the size of our starting infinite set. So the power set theorem still holds. Another thing to note is Schroeder-Bernstein. So Schroeder-Bernstein says that if we have if we have f from A to B is injective, and G from A to B is surjective, then there exists a function h from A to B that is bijective. Equivalently, if we have f from A to B, or we have f from A to B is injective, and G from B to A is injective, B to A, injective. Then, or F from surjective and G, B to A, surjective. And there exists H, A to B, bijective, meaning that these guys would be the same cardinality. There is a pretty long-winded proof for this. If you are interested, you can look it up, or I'll try to remember to post a link to it. But I just want to make sure that this makes intuitive sense for you guys, because bijective, if there's a bijective map, that means that the cardinality of A and is equal to the cardinality of B. What does this first thing say? A to B is injective and A to B is surjective. So A to B is injective implies that the cardinality of A is less than or equal to the cardinality of B. And cardinality, it's surjective means that the cardinality of A is greater than or equal to the cardinality of B. If we have both of these guys, then we have that the cardinalities are equal. Similarly, on this level, if we have A to B is injective and B to A is injective, that tells us also that A is less than or equal to B, or the cardinality of A is less than or equal to B, the cardinality of B, and that the second one is that the cardinality of B would be less than or equal to A, which is equivalent to this statement. And then this guy right here, surjective and surjective, just means that the cardinality of A would be greater than or equal to the cardinality of B, and here that the cardinality of B is going to be greater than the cardinality of A. Another thing which I just want to clarify in case anyone would be confused about, the cardinality, I've already implicitly said it, but we can have A be a proper subset of B and still have that the cardinality of A is equal to the cardinality of B. An example of this is the natural numbers are a proper subset. The natural numbers are a proper subset of the integers. But the cardinality of the naturals is equal to the cardinality of the integers. And the integers are a proper subset of the rationals, and they have the same cardinality as well. One more thing to note is that cardinality forms an equivalence class. So that means that having the same cardinality is transitive, reflexive, and also transitive, reflexive, and symmetric. So there we go.